fully see my screen. Do you see it?
Yeah.
This, what you see here, is the graphical user interface of the software RelaxIS 3. And so far, everything is empty because we haven't loaded data yet. This is the very first step that what I want to show you. So I have prepared data files or multiple different data files. So we have, for instance, here a data file coming from Biologic, from Autolab, from we also have some data files from Zana here, or we also have here something that I call unknown data file. You will see it in a few minutes what's this, and something that comes from a battery cycler. So how this works is you typically click here on the data file, and by drag and drop, like in case of the biologic file, you load it into the software and it's here.
Yeah.
And the same holds here, for instance, of course, for the Autolab file, or for the, or that's not what I wanted to show. This here, the data files from Zana, for instance. So you see I can also insert multiple data files. Or what I can also do is, if I have here, for instance, this cycling data here, I can just load. This will take now a little bit longer. This very large package of different data sets, this battery data that has been recorded using a special cycler. So let's see, it should be there in a few seconds. Now it's there. You see we have now multiple data files here loaded in the software. And if you have something looking like this, so for instance, if we have here a data file, if you click on this, which is just a text file consisting of different columns filled with values, like here you have a column like frequency, Z prime, Z double prime, temperature, thickness, area. So we also have here metadata in this case being contained in the data file. We can also try to load this one. Then a dialog opens where RelaxIS has some questions to us. So it wants to know what is, for instance, the column delimiter, the number format. And you see here, RelaxIS identified there's also some kind of header in this case. And we go, if you go now here to next, RelaxIS sorts the different data after columns. And each column has some kind of meaning. So first we know from the file that the first column is the frequency, followed by the real part of that, followed by the imaginary part of that, and some metadata like temperature, thickness, and area. And RelaxIS identifies the header and makes some kind of initial guess. So in this case, RelaxIS tells us, okay, it seems as if the first column is frequency, and yes, it's frequency. If this should not be the case, you can click here on the drop-down menu and click here on the correct meaning of this column. Once you have done this, you also can look into the data set itself. So you see here, it starts at 1 kilohertz, goes up to 100 kilohertz, then again 1 kilohertz. So we have multiple spectra in one file, and we can split this automatically in RelaxIS. This can be set here on the left side. Once we have done this, we can just say, okay, use this settings for all the files contained or to all the files that we want to import. And that's it. We have now also loaded this data. However, this was only the first step. So you see, we can just load multiple different data files or proprietary file formats, but also text file formats directly into RelaxIS, which is quite helpful because, you know, it's, if you go to the different laboratories, they don't have only a potentiostat from one brand. They have different brands, and each brand has its own proprietary file format. You have the MPR3 files from Biologic, you have the NOx files from Autolab, you have files from other manufacturers, and RelaxIS is an independent platform that can handle all the different file formats. And if there should be any new file format, because to be honest, we are not so aware of what other brands are there on the Asian market. We know that there are also local potentiostat manufacturers. We only need some kind of dummy file that we can then analyze, and then it will be embedded as a new file format, which can then be directly imported into RelaxIS. And the user also can do this by himself, because we also allow to have some kind of software development kit coming with RelaxIS. However, typically loading data is not the most difficult part, but it's quite convenient in RelaxIS. This is why I wanted to show you this. And the first part that I want to go through together with you through is what different plotting options we have in RelaxIS. So if you go, for instance, here to this battery data set here, you see typically when you load data, the first plot that appears is the Nyquist plot, because this is the most prominent one or the most popular one. But this can be changed in the settings because we also have other plots that are available, not only by default, not only the Nyquist plot, but also the Bode plot, where you have then Z prime and Z double minus Z double prime plotted against the frequency, or the Bode phase angle plot, where you have the modulus of Z and the phase angle of Z plotted against the frequency. This is possible. However, you also have quite user-specific options also. You can go here to this option X, Y1, Y2, and here you can define by your own what should be plotted on the X-axis, what should be plotted on the left Y-axis, and the right Y-axis. So you can tune or you can work here on what should be plotted, but in the end, typically, also based on my own experience, most users only use either Nyquist plot and or Bode plots, but these are there by default. And you can also switch between different transfer functions. It's called impedance spectroscopy. Therefore, typically people plot the impedance, but you can also calculate from the raw data other transfer functions. So you can also calculate the complex admittance and plot it, or you can calculate the complex capacitance or the complex elastance. This depends a little bit on the field your customer or your client is working in. So typically most people use impedance spectroscopy, but if you deal with people working in fields like dielectric spectroscopy, they might also be interested in elastance or modulus plots, or they might also be asking for admittance plots. So this is possible. But let us stay for now with the impedance. And here you see we only have this one graph, but we have a measured series of different data. So what would be interesting is to make just some kind of overlay plot. This is also possible. I go now into this list here in the lower middle part of this graphical user interface and mark maybe these 6 spectra here. And I can make some kind of combined data plot. And you see here that we now have multiple data being plotted together in one plot. And we also have a legend where we can always see what spectrum belongs, in this case, to which state of charge, so to which DC voltage. And here you can see, for instance, this case, when we go from high state of charge values to, in this case, which are quite to the upper limit, to lower values, then here this diameter of this semicircle here, which is under this curve, shrinks. That means in this case, for instance, the charge transfer resistance getting lower if you go from the highest state of charge values to a little bit lower state of charge values. So you can identify general trends when you make this overlay plots, and they are available in 2D, as you see here, but also in 3D. So here you have, for instance, now a 3D plot of this data. Okay, it's very close to each other, so you see almost an overlay except for here this part, but this is also possible. And irrespective of which plots or which data you plot in RelaxIS, you can always right-click on the graph. And in the graph, you see we have different, in this menu, you see we have different options. So you can, for instance, of course, zoom in, zoom out. You can also export the graph image. That's pretty nice because think of a situation you have gathered just a large amount of battery data, and you don't want to fit them right now, but you just want to show general trends. Then you can make an overlay plot, and then you can export the graph image for your report. And here you can export a graph image based on your predefined resolution, or you can just also copy it to clipboard. For instance, if you directly want to paste it into your PowerPoint presentation, you can create a file or also vector graphics. So this is all possible here. And what you can also do is, if you don't want to export the image, but you want just to export the data that you see here in this plot, this is also possible if you go here to export raw data, and then you can export the data that's plotted here and load it then, for instance, in Excel or Origin or whatever typical software you are using for creating nice plots. You might say, okay, Marcel, that's pretty nice. You have here just somehow some kind of limited amount of windows here in RelaxIS. This is true, but you can create new windows. For instance, you can go here to create new spectrum view. And if I want to also visualize the data in another representation, not only in the Nyquist plot, I can click here on plot view. And if I click here on plot view and then here in the select plot preset, I can also depict, for instance, the Bode plot, and then I can run through the data and I see always both. I can also create a third or fourth window, but this then depends on what size you have or what number of monitors you have, basically, or what's the size of your screen. This you can do. You can also create, once we have performed a fit, so now we haven't performed the fit, but later you can also show a window where you will always see the residuals of the fit, or what we call here info view, the statistics of the fit. Or if you want to add graphical elements, you can also visualize this. This here is pretty interesting. This is Grammar's chronic view. You can have a live Grammar's chronic view. I only have to work here on the settings. Okay, so you see here, the line is, you don't actually see the line much, but here you see the line going through the data points. This is a Grammar's chronic simulation, and the data points are the measured data. And if I go here now through this different data sets, you see here Grammar's chronic is fulfilled for most of them. Maybe not here. In this case, we have some issues with Grammar's chronic, but for most of the data set, we have Grammar's chronic being fulfilled. And what you also have is here, oh, sorry, I didn't want to close this window. Here, Grammar's chronic view, we can here also in Grammar's chronic view, you see, select here. I only, and for this battery data set, I have to minimize the number of time constants because otherwise we get some overfitting, what you see in the background for Grammar's chronic. And if I limit this, because we have here more than 700 data points, you get then the Grammar's chronic plot as it should look like. And we can also depict the residual plot, for instance, the relative residuals. And then you see here the relative residuals, or the difference between the Grammar's chronic simulation and your measured data. And then you can decide whether it makes sense to use the data or whether the quality is not sufficient enough. But here, as you have seen, you always need to check what is the amount of data. If you have such data sets like here with 700 plus data points, you have to minimize the number of time constants here in the setting to 10% in this case. If you go, for instance, to this data set here where you don't have so much data points, you need to increase the number of data points here, and then you get the Grammar's chronic result as you want to have it. So we have multiple options here. We can handle low amount of data, a large amount of data, and perform then this live Grammar's chronic test. And what you can also do is you can, if you go back to this data set, and we work here, for instance, on the create new spectrum view option, you can, instead of having a Grammar's chronic view, also a DRT view, where you can have a live DRT of all the data. It will just take a second because it needs to calculate the DRT, but I hope it will show it to you in a few seconds then. Because it's a pretty nice feature, because we can then just go through the data and have then the live DRT analysis. Let me just check. Interpolate data. Okay, this should work. Okay, here you see it now, the live DRT. And this is pretty cool because here I can also say, okay, we have some kind of polarization. I want to subtract this, then one of the peaks will be just kicked out. Okay, and then we have then here, if you go through the data set, you see here then the live DRT, which is really cool. So you see here, if I go through this, that one of the peaks just getting smaller. And then we can also see how this is working as a function of the SOC in this case. However, this is just a quick option to calculate the DRT. We have even more powerful options integrated in the software that I will show you later. For now, it's more like I've shown you now how to import data. I have shown to you how to plot data in different fashions. Now you would be maybe interested in seeing how I can fit data in RelaxIS. And fitting data in RelaxIS, like I need first to select the spectra or the data sets here from this list that I want to fit, because I first need to create some equivalent circuits model for fitting the data. And this I will do now. So I want to fit all this battery data, for instance. Let me just select the battery data here. And I want to fit this battery data with one and the same spectrum. I will give it a try. So I right click here and move it to a group. And each group is defined by some kind of equivalent circuit model. Since I haven't defined an equivalent circuit model now, or so far, I can just click here on New. And then this dialog opens. And I will now explain to you how to define equivalent circuits in RelaxIS. There are 3 different options for doing this. So I would say most complicated, but maybe also fastest options, if you are familiar with the nomenclature in RelaxIS, is that you can just write down the string defining the equivalent circuit model. You see here, I'm now here, you see these 2 input boxes. You see the left one with the 2 brackets. I will just give the group a name. I call this group, for instance, battery data set. And then I can just write down the equivalent circuit as follows. So I see here in the high frequency end, you have this non-ideal inductive behavior. This is typically described by an inductor and a resistor in parallel. So I'm just writing the abbreviations for the elements, what you see also on the right side here in this model quick reference. So I stands for inductor, R for resistor, C for capacitor, P for constant phase element. And I write both in brackets followed by each other. That means both are in parallel. Then I need some kind of resistor for the high frequency offset. Then I need 2 RCP elements for the 2 semicircles, and then I have at a low frequency range, I have some kind of polarization or diffusion behavior, and this will be now the equivalent circuit model. And you see it was quite quick for me to create this. However, this is not the only option. The next option would be you can just, I click now on clear. You can use these buttons here, and on each button you see a symbol for this equivalent circuit model. For instance, here the resistor, capacitor, inductor, and so on. And here you have 2 checkboxes, parallel or serial. And I can just say, okay, first I want to contact in parallel inductor and a resistor. Then I want in series, I want to have a resistor. Then here you have partial circuit elements like RCPEs. And then I can click here, for instance, into this and add this P. And this is also another option to just use these buttons here and click together the equivalent circuit model. And there's also another option. We have here a pre-made library of quite a lot of impedance of equivalent circuit models for fitting impedance data sorted after applications. So you see here, for instance, my favorite ones, then batteries, then bioimpedance, coatings, conductivity, corrosion, DSC, fuel cells, and so on. And you can just go into this section here and see if there's an equivalent circuit model that would always already be useful for fitting your data. Maybe this one looks not too far away, or where is it? Here it is, this one, but I go here to favorites, and then under favorites I have already predefined my equivalent circuit model, and I click on this and then I have it. This is pretty fast pretty convenient. And the nice thing is here you have the option to also add your own models to the library. You just need to click on Model Library, then Add Model to Library. Then I can say here, for instance, battery data set. I have here my equivalent circuit model. I need to put it into this box. Then I need to say or to define to which group this equivalent circuit model should belong to. In this case, it's favorites. I can make a comment like, this is the one and only ECM or stuff like this. And if there is some kind of source, so for instance, you found this equivalent circuit in a research paper, or this was just part of an internal, project, then you can also give a source here. For instance, you can give a DOI to a paper or a link to a locally stored file. And then you can click on OK. And once you will click on OK, it will just appear here. In this case under favorites. You can also remove models, ones that you don't want to have anymore. And you have another view of all models in the library. When I click here on List All Models, you can see that this window here opens. In this window here, you see we can here under category, we can define the different categories like batteries, bioimpedance, coatings, and you can see what is there. In batteries, we have most of the predefined models so far, and we have here the models. Then we have here for some of them a source like a DOI. You also have some kind of comment, and whenever you have some kind of DOI or local path, you can click here on this open link. For instance, think of situation, you are sitting together with your project partner and you have selected a quite specific equivalent circuit model for fitting your data. And this equivalent circuit model is also part of the library, and you selected this one because it is related to a publication where people did something quite similar to what you are doing. You can just click here on open link, and then you end up with the publication out of RelaxIS. This is also pretty nice because you don't need to search for this for long. However, let us just take now this equivalent circuit model as the one that we want to use for fitting our data, and I click now on OK. I have to say for which data this should be applied. In this case, the selected spectra from the list. And this is what happens now. On the left side, you see here we have now a list of 3 parameters, so 3 fit parameters for inductance, resistance, CPE values, and so on. We see here again the equivalent circuit model, and if we click on each of these parameters in this list, we see here to which it belongs, to which element. Then we see here on the lower left side, we see a list view, like we have now the group being called battery data set. And in this group, there is this data that can be described hopefully with this equivalent circuit model. And we have still the unassigned spectra like these that I have not, touched so far, where I haven't selected an equivalent circuit model for. And if you go into this group, I now want to fit my data. For fitting my data, I can go here to fitting. And under fitting, you see we have quite some options. And I will not go through all of them today because it's too long, but to the most prominent ones. So, for instance, what you have here, you have this data set here, which contains quite a lot of different spectra. And I want to first maybe give it a try and fit one of them, like this one, which is depicted here. And for this, I can go, for instance, for the autofit option. The autofit option in RelaxIS is a very powerful algorithm combining the standard algorithms from nonlinear fits with something that we developed in-house, where you have then some kind of genetic algorithm. That means RelaxIS tries to find arbitrarily starting parameters and give it a try for fitting the data set, and then it combines the best ones to build the next generation. It's also then fitting the data and so forth. And then after a number of generations, you are just killing all generations and start from new to find out if you always end up with the same optimum set of fit parameters. So it's like if you click here on the drop-down menu, you can say, I want to fit a single spectrum quite quick. That means the algorithm doesn't go too deep, or you want to fit it forward. That means the algorithm takes longer, and it's for multiple generation of different starting parameters to find out if you always go through the same, end up with the same minimum of the SSR. Then you have here this multi-quick and multi-forward options. That means RelaxIS takes all the data sets that are in this group and fits them together at one time. And then you have the custom autofit option where you can really work on the different settings of the algorithm. So it's really transparent in this regard. We are describing also the algorithm in detail in the manual. And here you can work on the different settings of the algorithm. And you have here just here in the next to each of these settings, you have also these small boxes with this question mark. And if you click on the question mark, you always get here also such messages describing, in this case, what this parameter is for. For instance, if I click here on maximum generations, it's telling me, okay, this value defines after how many generations the algorithm will stop. Or population size defines the size of population. That means how many parallel sets of parameters are evaluated and so on. So it doesn't, it's not always needed to go back to the manual. You always have such small helpful buttons here next to the parameters, for instance. However, in this case, I will just give it a try and hopefully it works to just perform a single fit. Let me just check. I would say good enough. You see here the fit. This is the line through the data points. On the left side, you see also that the fit uncertainties are all in green. That means that the fit error or the fit uncertainty is quite low. However, I could not go here for step by step through all the data. This would take some time, or end up with such situations where maybe you have to redo this to get the best fit. What I can do instead is I can also start a batch fit. Batch fit means that RelaxIS runs through the complete data set and tries to fit all the data. And we will just start this. However, this might take maybe 2 minutes. Let me just see, because it's a huge amount of data. And how this works is you go here to batch fit and say, okay, I want to start at this graph. And I would like to use this fit results as starting parameters for the next spectrum. And I want to go in the list downwards. This is what happens now. You see here, RelaxIS is going now through all the 202 data sets, and you see the counter. It takes a while, but here it's fully automated. So you can just take a cup of coffee while the RelaxIS is doing your task. And the maximum set of data or number of data set, what I have used so far has had 80,000 battery spectra. This took then quite a while, but it was then fully automatically running through this, which is then quite useful. Once this has been done, I want then to show you what you can do then with the fit results. So we are almost then at 25%. Of all spectra. So you see here the counter, it's now 60, 61, 62, and so on. And then, as mentioned, I will show you how you can then use, for instance, the results for the resistance or the capacitance value, for instance, by plotting them against the SOC or SIH if this is given, because it's also possible in RelaxIS. So sorry that this takes a while. I could have also limited the number of data sets, but I really wanted to show you that there is actually no limit. I can also increase the number of data files to, as mentioned, 80,000, but then it takes really long. But you don't have to do it by yourself. RelaxIS is doing that job. Okay. So only a few.
It's okay.
Only 1 minute left. Yeah, maybe the next time I use maybe instead of 200 only 100 spectra, but yeah. We are almost there. And you see always here also a small preview to just check if the fit works more or less. So for instance, we would see if the fit would not work, we would see that this fit line, which is here slightly in green, would be off and would not go through the data points. But so far it seems as if this is working pretty well. And now only 30 spectra left. And you also see how this is quite interesting also, you see how the impedance spectrum changes with SOC. You see now the charge transfer is getting larger, the diameter here is getting larger. It's also quite nice to see this while you're waiting for the results. Yeah, so far so good. Now RelaxIS has finished this job. And what you have here now is the complete data set has been fitted. You see it here. And you see here on the right side, there's still this empty window where you only have the RelaxIS logo. This is the so-called result preview. In the result preview, you can do some secondary analysis. So here you can really plot the fit results. For doing so, you go here to data setup. Then you can say, okay, what is the interesting quantity or parameter I want to plot anything against? In this case, it might be the DC voltage, which is related then to the SOC. You might also have the SOC value. So you see here, we have quite some options where you can plot data against. Then we have only one data set, so we don't need to split data. And then here you have this list. This list is sorted after the group. So you have the unassigned spectra and you have this battery data set. And the battery data set, you can plot all the three parameters. For instance, let us just plot maybe resistance 2 or resistance 3 or maybe resistance 4. Resistance 4, for instance, shows this behavior here. You see here the DC voltage. Maybe this very first data point doesn't have the right index or the right DC voltage in this column, but you see here quite nicely how this goes. So you see if this is the charge transfer resistance, then at very low SOC values, the charge transfer resistance goes significantly up. Then you have here this broad range of different DC voltages or SOC values where the charge transfer resistance more or less stable. And then for high SOC values, it goes up again. And this is pretty nice and pretty interesting to see this here when you have fitted all the data to just see here also how the different values behave. And what you see here, for instance, is the resistance 1 or the resistance 2. The resistance 2 might be related to the electrolyte conductivity or the serial resistance and also all the connections to the cell. And you see this value is more or less stable if you have a look here at the value range, but also shows some kind of SOC dependent behavior. So this is quite nice that you can just plot this data here after evaluating this fit. I want to show you using another data set what else you can do. So we have here also, if I go back to the unassigned spectra, we have here this conductivity measurement series. This is just impedance data of a liquid electrolyte at different temperatures. So you see here 10 degrees C, 15, 20, and so on. And I would just like select these data points here and also right click here and say, I want this to be moved to a new group. This group should now be called conductivity series and then model 1. I clear this and I just say, okay, first want to give it a try and select as equivalent circuit model a resistor followed by CPE for this data set. And then I want again to perform a fit. In this case, I could also again start a single quick and then go for batch fit. But I can also in this case use, for instance, because it's not too many data sets, I want to go here for a multi-quick or multi-furrow auto fit. That means that RelaxIS goes now through this group and performs a fit of all the data sets at one time. That's it. We have now performed a fit and you see it worked quite well for the low temperature, so 10, 15, 20 degrees C. But if we go to higher temperatures, you see it's a little bit off, in particular the mid and low frequency part. Therefore, it would make sense to just use the same data set and fit it with another equivalent circuit and compare the results. This is possible in RelaxIS. I can just mark all the spectra here and say not move spectra to group, but copy spectra to group, and in this case, a new one. And I would just use a group that's slightly different regarding the equivalent circuit model. In this case, a resistor followed by an RCPE, taking into account the low temperature, the low frequency curvature. If I do this, then I open another group. You see on the left side, we have here this group, which is called Conductivity Series Model 1. And we have this new equivalent circuit model with this resistor in parallel to the CPE at the interface. And then we have here this simple model. And I just go here into this. I perform a single fit and then a batch fit. That's it. You see how fast this is, and you see now the data is fitted better, in particular in the low and mid frequency range. And the nice thing now is you can just compare the results. You can go here on the right side to the result preview and say, okay, I want to plot my data against the temperature. And I want to go here into the conductivity series model 1 and 2. I should have renamed this into model 2, but anyhow. And you can select here resistor 1. Then you see here the resistance as a function of the temperature for the simple model. And we need to select then here also, after selecting a split by model, the resistance one coming from the more complicated model. And the interesting thing is, you see, it depends in this case on the equivalent circuit model that I selected, what value of the resistance I get. And in the end, it depends also on the selected model what conductivity I can then calculate in the end. And here I can then visualize the difference between the two models. So the red data points come from the more complicated model for the resistor and the black one for the easier model. However, let us just assume I will just select the more complicated model, so this. And what I can do now in RelaxIS, I can click on this small button, Result Evaluation, and I can just say I want to evaluate the temperature behavior in RelaxIS. We also have other options here. And then I can say I have measured the temperature and decrease C. And I can say I want to have a Arrhenius fit. And then I can perform an Arrhenius fit and I get directly the pre-exponential factor and the activation energy out of RelaxIS, which is pretty nice. Or I see maybe it's not Arrhenius, maybe Vogel-Fulcher-Tammann. Then I can also use this one and get parameters here. So you can really load data, you can fit the data, you can work then also on the fit results in RelaxIS to perform the secondary analysis. However, just two final things in regarding the fitting options. I go back to the unassigned spectra and I want to look more into this spectrum now. You see here, it looks also more or less like a battery spectrum. Yeah, it is a battery spectrum, but the high frequency part seems to be a little bit problematic. We can check this under data and quality. We have here the more extended Kramers-Kronig test. And I want to perform a Kramers-Kronig analysis of the selected spectrum. And I want to perform a complex fit. I would like to take into account the low frequency capacitive behavior and the high frequency inductive behavior. And I see here, when I perform a Kramers-Kronig analysis, the line goes very nicely through all the data points except for the high frequency part. You see it here. That means the high frequency part seems to be problematic, and I can also visualize this if I go here to residual plot and maybe to the relative one. And then I can here see that for low and mid frequencies, the relative residuals are very, very low. That means here the data seems to be valid. But for all frequencies above 10 kilohertz, you see here that we have a significant increase of the residuals. That means or tells us that Kramers-Kronig is not working at the high frequency part, so most likely either linearity, causality, or stability of the system are not fulfilled. So, or with other words, I cannot fit the complete frequency range, so I need to limit this to selected frequencies. I can do so if I go here to fitting. I can go here on the left side, upper left side, to select range or select active data points. If I go to select range, I can just click here on the highest data point that I still want to consider for the fit, and then on the lowest data point. And you see what happens is that here some data points are grayed out at the high frequency part, and these are not deleted or removed, but they are not considered for the fit. The other options that I have, I can select all active again, I can also go here to select active data points. And in select active data points, I can just, for instance, draw a window here, then they are removed. Or I can click again on them or on selected one and can just say which data point should be removed or should be taken into account for the fit. This is also quite nice. Let us maybe for now just deselect this one, maybe also this one. And then I can just say, okay, once I've selected or worked on the frequency range, maybe this one here, I can just leave there maybe. So here again, let me just check it again here. Maybe this would be a good way. No, this one maybe too. Okay, let us just give it a try. And then once I've done this, I can just say, okay, move this spectrum to a group, a new one. In this case, I would say it's also some kind of battery. It's in this case a solid state battery. And then I can just say, okay, here you need definitely to consider again an inductor. Although I've removed the data points or excluded them from the fit, the inductive contribution is still there. Then I have maybe 1, 2, 3 RCPEs and then a low frequency CPE. And I want to fit the data, the selected one. Then I opened a new group, which is now called battery SSB and which contains this data set. And hopefully it works. Let us just give it a try. This case, not so good. Let us just redo the autofit. I know why. I forgot one element. Sorry. I need to change the equivalent circuit model because I just forgot the high frequency offset. So now it's better. Without taking this into account, the fit cannot work. So let us just redo. Better. So you now see that the fit is working. And however, what we could now also check is, for instance, we could go to weighing methods and see if another weighing methods. So far we haven't performed any weighing. If this is better, for instance, if we go for proportional weighing, if it's better, let me just check. Yeah, it's better. So in this case, so what means weighing? So weighting means you can just take the raw data of your measured impedance and you can just perform a fit. However, since the target or the goal of all nonlinear fits is to minimize the SSR, that means mathematically the algorithm will try to improve the SSR or reduce or minimize the SSR for the high impedance values more than for the low impedance values. So that means your spectrum is roughly said better fitted at the high impedance end, so the low frequency typically, and not at the high frequency end. And for considering all data points equally, you can just go for weighting options. That means you normalize the impedance data by dividing them, for instance, by the modulus or Z prime or Z double prime values, so that you can just consider all data points equally for minimizing the SSR. And therefore, in this case, if I go here to weighting methods, to drop-down menu, the proportional weighing work better than the non-weighing. So you saw now what you can do in terms of limiting the frequency range and weighting options. Another option is you can also use graphical elements for initializing the fit. For instance, you see on the right side, we have add circle, add line, and add shape by selection. You can add a circle, for instance, like this. You can also add, if you're a little bit lazy, you can just use this tool for adding circles. You can add lines. You might now ask, okay, Marcel, it's nice that you can draw circles and lines, but what is this for? It has a reason why I'm doing this. So if you go here to the left side above the parameter explorer, you see hopefully where my mouse is, there are now the 5 different things that you can extract graphically from this adding circles and lines tool. So you can now click here on the offset, for instance, and drag it down to resistor 1. You can click here on circle 1 and drag it down to resistor 2 and CPE 1. And then here circle 2 circle 3 and the line, which is giving me the starting parameters for the CPE. And it's like you take then the diameter of the semicircles and where the center is, and you take also the slope of the line to get starting parameters for all the parameters here in this list. And then I can just click here on single fit and hopefully it works. I'm not sure. But if I click here on single fit, it works. And you see I haven't performed any auto fit. I have now graphically initialized the fit procedure, which is also possible in RelaxIS. And now I can remove all objects. However, now I've told you quite a lot about what options you have in terms of fitting. There are only 2 different topics or 3 different topics left. One is you might be interested also in learning more about what do you have in terms of fit results. So what can I learn from the fit results? Here's this tag. And under this tag here, I can just click here on fit information. So I get all the fit information for all the spectra here. So the matrices and all the statistics, this can be exported. So the SSR, chi-squared and all this, but also here also the matrices. Then I can here also visualize the residuals of the fit. This is possible. I can also perform some bootstrap error estimation. This is a pretty nice tool. So you might ask, okay, Marcel, you have performed now an autofit. But what would happen if I redo the autofit? Will I always end up with the same results? And the answer is no, because I have some kind of uncertainty for my fit parameters, which is here on the left side. You see this column called fit error, which is now in green, more or less. But you see some of them have a higher uncertainty, some have a lower uncertainty. And if I run now through this bootstrap error estimator, I can say, okay, RelaxIS, please do the autofit 250 times in this case. I can also say 150 times or so, or more. And then just visualize then what is the distribution of each fit parameter value. You see here, this is faster in this case, and we are almost done. And then I can show you what you get out of this. Now there is it. So we have here a drop-down menu where we can just visualize the results. For instance, if we go for resistance 1, we see that if we perform the autofit 250 times, most of the time we get something around 37 ohms, but there might be situations where we get almost 40 or 31 or 30 ohms. But if you go, for instance, to parameters where we have a higher uncertainty, maybe this one or this one here, you see you have even a broader distribution, and this is quite helpful to understand better what is can you really rely on your fit. You might have situations, and this is really not so rare, that you might have 2 maxima. And this is the case if there are maybe 2 different models or 2 different ways for fitting your data. And this is quite interesting here if you can just visualize this. This is quite a nice feature. And another nice feature is we have the parameter influence test. That means you can visualize within, roughly said, within which frequency range each parameter plays a dominant role. So for instance, you see here inductance. The inductance is dominating the high frequency part. And if I go to the series resistance, also dominating the high frequency part, but it's also contributing to the mid and low frequency. When you go to resistance 3, it doesn't play a role at high frequencies, but in the mid frequency range, and this is also quite useful. And before I go to DRT, I only want to show you one additional feature, which is quite nice. So you might have situations where you don't have any idea at all which equivalent circuit you should need or take for fitting your data. In this case, you can go to data and quality and to model screening. And under model screening, you can just say, okay, RelaxIS, take every equivalent circuit model that we have in the library, or just selected one, so I can also deselect some of them, and perform autofits, and then create some kind of high score list. And the high score list, I will just start this, is created in the way as follows. So RelaxIS sorts the equivalent circuit models after their SSR. So the lower the SSR, so the sum of squared residuals, like always in nonlinear fits, the better. However, you know that one disadvantage in impedance spectroscopy is that you might have situations where more than one equivalent circuit model might work for fitting your data. And in RelaxIS, here in this model screening tool, we have introduced some kind of penalty factor. That means we don't sort the equivalent circuit models after their SSR, but after their so-called score. The score is nothing else than the sum of squared residuals multiplied by the number of free parameters to the power of a penalty factor. Or roughly said, if two equivalent circuit models seem to be equally well suited for fitting your data, the one is preferred over the other that has the lower number of free fit parameters. So the simpler, the better. And if you just stop this now, because this would not take a while, you see that the topmost position of our screening tool already suggests an equivalent circuit model that is very close to the one that we have just taken. There are only two differences. We don't have here in this suggested model, we don't have a series inductance. And we have more a partial Randall circuit here because the CPE3 is incorporated in this RCPE instead of being series. But it's very close and very helpful because this might be a very good starting point for getting a better idea which equivalent circuit might work for fitting your data. And this can then be applied and used for fitting your data. However, now I want to give you some kind of overview about the DRT functionalities, and this is I would say, the last more extensive point for today. So we have here this under data and quality, you find DRT. And if I go to DRT, I can say in this case the selected spectrum, which is only this one here. And then this here opens where I need to make some settings. I need to say, okay, what should happen to the low frequency polarization, which is there. I can say, for instance, subtract the polarization. Then I see also we have some kind of inductivity at high frequencies, therefore fit inductivity. Then I need to do also the job to select the right lambda and shape factor values. For now, I leave it at 0.01 or 0.5. We have some options in RelaxIS to optimize this, which I will show you in a few minutes. And then I can go here to next, and this is the DRT. So you see here we have 3 overlapping semicircles, and then DRT we get 3 peaks, so seems to be quite reasonable. And what I can do now in RelaxIS is I can go here to peak picking. I can pick peaks, I can integrate peaks, or I can do peak fitting. Peak fitting is my favorite. I can just need to move these green bars here, and I need to add some kind of starting peaks like this and this one here. Then I click here on accept. Then I fitted my spectrum, and I can export a list, and in the list I get the tau values and the area, which is actually the resistance belonging to each process. So that means I have here 3 processes. One has a time constant of 10 microseconds, one has a time constant of 0.2 milliseconds, and another one of 2 milliseconds. And I have here a related area of 25 ohms, 38 ohms, and 50.6 ohms. The question is, are these values meaningful? And this I will just quickly close DRT to show you another options what you can have, for getting time constants. So for instance, you can go here back again into this conventional fit and copy the spectrum to a new group. And in this new group, I would just like to exchange the RCPEs by so-called set arc elements. And the set arc element is mathematically the same like an RCPE, but it provides you directly based on a conventional fit with the tau value. So you can get the tau value as a result of a fit. And I would just like to give it a try and fit the data in this regard. Hopefully it works. Let us just see. Yeah. And here we see now on the left side, we get also from this conventional fit a tau value of 10 microseconds. then 0.2 milliseconds and 0.3 and 3 milliseconds. And this is quite well in line with the DRT result, because I can go back to DRT, perform the DRT again based on the settings we have already made. Go again to peak fitting. Add this here, here, and here. Go to the list, and then you see here on the left side, Zag tau 1 is 1.2 to the power of -5 seconds. It's the same here. Zag tau 2 is 0.25 milliseconds. Is more or less the same order of magnitude here. And then tau 3 is 2.8 milliseconds, and here 2 milliseconds, also the same order of magnitude. And also the related resistance values are of the same order of magnitude. This is a very good cross-check. If your DRT provides you with meaningful results, if you can also handle the spectrum using the conventional equivalent circuit model approach and exchange RCPEs by set arc elements, and if you get comparable values for the tau values and resistance values, then you can rely definitely on your DRT. However, we have now evaluated the DRT. As mentioned, we could also integrate just peaks or pick peaks, but I will not show this now. The thing is the DRT really the true DRT? Because if I go back, this I can do. I can also work, for instance, on the lambda value in a way that I just minimize the lambda value. So I add it just to 0, so that's now 0.0001, the lambda value. And now I get something like this. And you can ask me, okay, Marcel, what is now the true DRT? And I can tell you both are correct, because the DRT is just some mathematical result being dependent on what conditions you provided. And the lambda value is just some regularization parameter that mathematically defines the outcome of DRT. So mathematically, both results are true, but in the end, what is physically meaningful? And we have a few options in RelaxIS. One I have already shown to you. One is the comparison of the set arc element with the DRT outcome. The other one, for instance, is here. If I go here to this Monte Carlo statistics. In the Monte Carlo statistics, I can just say, okay, vary, please, RelaxIS, the lambda value from 1 to the power of 4, for instance, to 1, so quite broad range, with 5 different lambda values per decade, and just show me what is the how to say it, range of DRTs that I get depending on the lambda value. And this is currently running. It will be finished in a few seconds. And then you will see something like a mean DRT with a trust band. And then what is maybe the minimum or maximum. So you see here in gray what is more or less the correct or real DRT, because this is something that we get over the complete range. And then you get something like a minimum or maximum DRT. So this is always good. So you see here again, we have these 3 peaks. And if you perform this over broad lambda value range, then you get here more or less this average lambda value, this average DRT. And then this is something you can then just compare with the lambda value that you have selected. Another feature that we have in RelaxIS to check if this DRT is meaningful, you can go to show reproduction. In this case, RelaxIS pretends that you would have never measured the impedance spectrum, but would have started from the DRT, and it makes an overlay of the spectrum here in red, which you can back calculate starting from the DRT with the real spectrum. And what you see is for the mid and low frequency, frequency range, and more or less for the high frequency range, it's okay. But for the low frequency range, you have here, you are off. And the reason for this is that I just excluded the polarization region from the DRT. If I would include this, let us just check what will happen. Then it would be better, the reproduction. But if we go then here to the DRT plot, you see we will then have additional peaks. In particular, this peak here, this large peak, and this is just because we have included the polarization in the DRT. just quickly, I want to show you what else you can do. You can also go here to, let me just give it a try if it also works here now. For this battery data set, for instance, we make here the DRT for the selected spectra. We want to, again, ignore, we want to subtract polarization, we want to fit under activity. And here we get then this battery data set, which is from an LG battery. And what we can do here, we have now multiple data sets. We can just make an overlay between different DRTs. And you see here, maybe I can even increase the number. This would be maybe even better. Let me just increase the number here. Here. Now it's 36 spectra. They evaluated all. And a pretty nice thing, what I can now do is I can now select multiple of them and I can make an overlay, and you see as a function of SOC, the DRT changes significantly, and I can not only show this in 2D, but also in 3D, which is quite nice also for publications. Yes, this was quite a lot. One thing would maybe just to quickly mention this, but I have forgotten to open this. I need to simulator. Where is it? Here. If you have RelaxIS, you not only have at a RelaxIS license, you not only have the RelaxIS of the suite, you also have a circuit simulator. I just want to show it quickly. But this is very nice tool for educational purpose and also for studying then the behavior of different equivalent circuit models. While this is starting, I can explain to you that using the circuit simulator, you can just develop equivalent circuit models, like for instance, this one here, and you can say, okay, I have a circuit looking like, for instance, this one. And I can now go here, for instance, here, and can just model then the impedance behavior of this equivalent circuit model based on different here values for the resistance or capacitance. Okay, my example here was not the best one because you don't see that much in the Nyquist plot. Maybe I can just remove all of them and select a new one where you can see more, maybe 2 RCPEs, then it's better. Maybe this one from value ranges, circuits, or value list. Let us just take maybe value list. Then we go here to this equivalent circuit model, and I would like maybe just to select this one. And then we go here to continue and say, okay, I want to have here this, maybe here CPE with 10 to the power of -9 and a higher resistance value, maybe then 10 to the power of -6 and an even higher one. And then continue. We want to add a range, maybe for resistance 3 at range, and maybe this range should be 10 to the power of 4 to 10 to the power of 6, 10 points. Finish. And then you can just simulate this. This is pretty nice. You can just simulate in different spectra. You see here, for instance, always this small semicircle. And you can simulate this. You can also add some, you can change the frequency limits here. For instance, here to show how this works, like if you have then other frequency limits here, stuff like this. You can also add some noise. Where is it? Noise to show how it should not look like, or add a noise also to phase angle. And this is not the best spectrum now, but here this is how it should look like. So this is for training purpose, educational purpose, and it also comes together with RelaxIS. Okay, so this was all that I wanted to show you for today. Do you have any questions regarding the features?
Not, no, until now.